Hi there, and welcome to the video for section 2.1 on the topic of matrix addition, scalar multiplication, and matrix multiplication. So the idea in this video is that we want to talk about matrices a lot more. We've seen how to use an augmented matrix to help you solve a system of equations, but in this video we want to talk about matrices more as a topic all their own, and then we will fold in a sort of bigger picture of linear systems using these ideas of matrices. So let's jump in here. Basic stuff to start out, just talking about notation and some terminology. Given an M by N matrix, so that means it has M columns and, M rows and N columns. Given an M by N matrix A, we denote the entry in the ith row and jth column of A as lowercase aij, or you might notice somewhat often I will represent that as brackets around capital A with that little ij subscript. So all we're saying is that if I've got a matrix of numbers, something like this, if we want to identify the entries here, we have a numbering system, right? We number the rows. This would be the I equals 1 row, this would be the I equals 2 row, and columns, this would be j equals 1 and j equals 2 for the column. So for example, if I want to say what this entry is here, the way I would describe this, if this is matrix A, for example, we've described this entry here, since it's in the second row and first column, if this matrix is A, we'd write this little entry in the bottom left corner as a brackets around it 2, 1, I value of 2, j value of 1, or equivalently lowercase a 2, 1. In that case, for this matrix example, 1 was the value of that entry. That's that value right in the lower left corner. So that's just how we describe the entries in a general way. We have this sort of numbering system, the ij subscript. We say a matrix A is a square matrix if m equals n, if the number of rows is the same as the number of columns, right? So this matrix I happen to write down here, 2, 1, 1, 2, that's an example of a square matrix. And the elements on the main diagonal of a square matrix A are the elements A1, 1, so that's the element in the first row, first column. That's the 2 that was up here before I kind of got my picture to be a mess here. That's the 2 that was sitting here. A2, 2, that's this other 2 sitting here because that's in the second row, second column. I equals 2, j equals 2. And so we're seeing that when we look at the element with the row and column index, that's what we call the I and j respectively. If we look at an element with the row and column index equal, that's an element along this main diagonal going from top left of the matrix to bottom right of the matrix. In this little toy example I wrote down, the main diagonal elements are just 2 and 2. Okay, so if we refer to main diagonal elements, that's what we're talking about. We usually only talk about that for a square matrix, because it will go from top left corner to bottom right corner in the case of a square matrix. A few more definitions here. Two matrices A and B are equal. We need to know what it means for matrices to be equal. They're equal if they are the same size, first of all, they have to be compatible sizes, and Aij equals Bij for all I and j values that are valid, meaning every row index and column index, if we put the same indices on A and B, we get the same entry, right? So we're just saying entry-wise, they have to be equal. In order for two matrices to be equal, all of their entries have to be equal. Pretty simple. Now to define addition of two matrices, again, this is going to seem very simple. Given matrices A and B of equal size again, and that's important, have to have equal size to add them. We define their sum, A plus B, to be the matrix that you get by adding their corresponding elements. For example, if you say the sum of these is some matrix C, then Cij, the ijth element of that sum, is just the sum of the ijth elements of A and B, right? Aij plus Bij. You could write this in a slightly different notation with those brackets. You could say the ijth element of the sum equals the ijth element of A plus the ijth element of B. And this is really showing you why I like this bracket notation, because if I didn't have this bracket notation, I have to do something like I did at the previous line. I have to say, define a new matrix that equals the sum, then I can say what the entries of that new matrix are in terms of the entries of the other matrices. I get to cut out all this business about this C matrix if I use that bracket notation, which is kind of nice. Another definition here, we defined addition of matrices. We also want to define scalar multiplication, or a scalar multiple of a matrix. So given a matrix A and a scalar C, the scalar multiple of C by A is denoted CA. And it's just the matrix obtained by multiplying each element of A by that scalar C. So in this kind of clunky notation, if you let B equal the scalar multiple CA, then the ijth element of that result is just C times the ijth element of A. So each element each ijth element of A just gets multiplied by that scalar. Again, we're seeing how the bracket notation for these matrices is a little simpler. We can just write the ijth element of CA equals C times the ijth element of A. We also, now that we have this idea of a scalar multiple, it's a pretty natural place to introduce the negative of a matrix. We're going to define, given a matrix C, we're going to define negative of that matrix C, so just denoted negative C, to really just be -1 times C, right? It's just a scalar multiple by -1. So that's how we're going to define a negative, which automatically gives us a nice way to define subtraction. We knew how to add. You might have guessed you can subtract the same way. If you follow this definition of a negative and think of subtraction as adding a negative, it does in fact turn out that to subtract matrices, you just subtract entry-wise, right? Subtract the corresponding entries, just like you add them to take a sum. So let's go through a couple little toy problems here, just basic matrix arithmetic and a little matrix algebra. Given these matrices, A equals 1, 2, 3 in the first row, 2, 1, 0 in the second row. B equals 2, 2, 3 in the first row, -1, 1 in the second row. C equals 1, 1 in the first row, 2, 1 in the last row. And D equals 2, 2, 4, 2. So we have these given matrices. We're told if 3A minus 2X equals matrix B, find that matrix X in this equation, right? We know what the matrix A is. We know what the matrix B is. We want to use some matrix algebra to actually solve for that unknown matrix X. So I'm going to do this over on the side here. This won't be too bad. We just need to know what A and B are and that equation we're starting with. 3A minus 2, slant here. 3A minus 2X. That's a matrix X. I usually write those with this sort of symbol for a capital X. Equals B. So before I plug in matrices A and B, I mean, you could do that, but before I do that, I think it's smarter just to use a little bit of matrix algebra, which is in many ways very similar to scalar algebra, regular algebra you've always learned. For example, here we can subtract matrix 3A from both sides, and 3A minus 3A just is a matrix full of zeros. So we don't have to write anything here. This just cancels itself out. Because a zero matrix applied with any other matrix, like subtracted by 2x, will not really change the -2x. Right? It's like you're taking 0 minus each entry of 2x. That's just -2 times whatever x is. But on this side, we have b minus 3a. You can take a scalar and to get rid of it, multiply by the reciprocal scalar, so -1/2 on both sides. So these cancel, and we're left just with matrix X equals -1/2, I put it out front instead, b minus 3a. And now that I've got a nice expression for what X is, let me plug in these matrices B and A. This isn't so bad now. B, give myself a little more space here. Matrix B is 2, 2, 3, negative 1, 1, 1. We're subtracting 3 times the matrix A, which is 1, 2, 3, 2, 1, 0. All right, just looking back over here, these given matrices, A and B. So this is going to be very easy. I'll go ahead and just copying this for now. I will take that negative 3 here and multiply it into this matrix, which really means, remember, it's just multiplying every element of the matrix. I should be careful how I say that. I'm taking the 3 itself. I'm leaving the negative outside. And what do we have? I'll go ahead and subtract these matrices. We know how to do that now. We know that subtraction of matrices is just applied element-wise, right? Corresponding elements. So in the top left corner, 2 minus 3 is negative 1. Next entry in the first row would be 2 minus 6, negative 4. 3 minus 9 is negative 6. Negative 1 minus 6 is negative 7 in the bottom left corner. 1 minus 3 is negative 2, and 1 minus 0 is 1. I guess I don't even need my parentheses now. And we multiply that through. Looks like we have positive 1/2, positive 2, positive 3, positive 7 halves, positive 1, and negative 1/2. So that's what x equals. So the point of this exercise is just to show that you have some freedom to use rules of algebra on these matrices. You just want to be sure you understand the limitations to those rules, which we'll see a little bit more of shortly in this video. So for this next part of this example, let's find a scalar gamma here. Sorry, my writing's not perfect here, a little crammed in there. Find scalar gamma so that gamma times, it's a scalar gamma, times matrix C equals matrix 4 times D. If it's possible for those two to be equal. So let's see what this is really saying. We're taking gamma times our C matrix equals 4 times our D matrix. And what do we do here? Right, you're trying to solve for this scalar, so it might be kind of tricky. What I would do is just express both sides as a single matrix without the scalars out front. In other words, incorporate those scalars into both sides. Multiply the gamma through this matrix. And multiply the 4 through this matrix. And what do we get out? By equality of matrices, in order for this equation to be true, we must have each corresponding entry is equal. So according to the top left corners, gamma must equal 8. Gamma from the left side must equal 8 on the right side. The next entry in the top row is going to give us the same equation. So nothing contradictory, nothing new though. The bottom left corners are going to give us 2 gamma equals 16, which again does just say that gamma equals 8. And finally, the bottom right corners again agree that for the two matrices to be equal, gamma has to be 8. So we can see that yes, it is possible for these two to be equal, only if gamma is 8. Right, so kind of just seeing what's really sitting on both sides and equating the components. You could very well have two different matrices sitting here where it's impossible to solve this. We're unpacking each of these equalities of corresponding elements would give you incompatible equations. Maybe gamma equals 8 and gamma equals 2. Both can't be true, but since all the equations gave us the same result, we know it does work, gives us equality in this equation, makes the equation true if gamma is 8. So let's go on to another, or go further with this, and talk finally about matrix multiplication. We've talked about how to add matrices. We've talked about how to take a scalar multiple of two matrices, or of a matrix. From that, we got how to take a negative and how to subtract. And we saw that really kind of unlocked the door to a lot of matrix algebra. But what we've not seen is how to multiply a matrix with a matrix. And really, that's because we haven't defined such a thing. Matrix multiplication hasn't come up yet. But here we're going to try to figure out well, we're not going to try to figure it out. We're going to write down a common definition of matrix multiplication and see how that definition just happens to be very useful for analyzing systems of equations. So you might always, if you've seen this before, or if you haven't, as you watch, you might start to think, this sure seems like a strange way to multiply two matrices. It's not going to be completely intuitive, possibly. So you might be asking, why are we insisting that two matrices have to be multiplied in such a weird way? Well, it turns out it's just useful to define it this way. If you had a different application in mind and you weren't solving linear systems, maybe a different sort of matrix product would be useful to define. But this one, the most common one, the one we're going to see, is useful for analyzing linear systems of equations, as we'll see. So let's get into it. How do we multiply matrices? Well, here's in words how you were going to do it, and we'll see with examples to clarify, to make it more concrete. Given matrices A of size m by r and B size r by n, first of all, notice that we're saying A has as many columns as B has rows, right? The R here in the size of A is the number of columns. The R here in the size B is the number of rows of B. So A has as many columns as B has rows, and that's crucial. We have to have that. So given these matrices of these very specific sizes related to each other, then the matrix product C equals AB, so the product of A and B, exists, meaning that if you don't have these dimensions, it doesn't exist, and has size m by n. And it turns out when you take this product, the ijth element of the resulting matrix, C here, is obtained by adding, and follow this carefully, adding the pairwise products, the corresponding entries of the ith row of A with the jth column of B. Now, if you're like me, you read that and your head sort of spins and you don't know what we're saying. It's a dense little statement in words, but I think in symbols all laid out and in actual examples, it becomes clear what we're saying. And if you've seen this before, maybe it's very clear what we're saying already. Right, so we're saying that if I multiply these matrices, A and B, let's actually look below for this. If I multiply these matrices A and B to get the ijth entry of the result matrix, right? The resulting matrix has as many rows as A and as many columns as B, right? So m by n, rows of A, columns of B. That's how many the matrix product has. So the ijth entry of that matrix product is the result of taking the ith row of A, which with the usual numbering system for those entries of A would have this sort of form, right? In the ith row of A, it would be row index I, column index 1, since you're in the first column of the ith row. The next entry in that row would be AI2, so you're in the second column, still in the ith row. Then AI3, third column, ith row, all the way out to AIR, where you're in the R column, that's the last column, but still in the ith row. Now the jth column of B looks like you're taking all the rows that sit in that jth column. So B1J, B2J, all the way down to BRJ. First row jth column, second row jth column, all the way down to the last row, but still in the jth column, picking up all those entries that have a jth column here. Might seem strange using letters for these instead of specifying numbers for which row and column you're in. This is a good way to think of it generally. So this is sort of what your ith row of A would look like. This is what your jth column of B would look like. All we're saying is that to get the ijth element of C, so the element of the ith row, jth column of C, the matrix of these two products, you want to think of sort of, maybe you've seen a dot product before. This looks a lot like a dot product of these two things. You want to just think of taking this column and sort of laying it over the top of the row. So it looks like B1J, B2J, all the way out to BRJ. Multiply these corresponding entries and add the results. Multiply, B3J here, multiply those, multiply these, and add the results up. That's what we have written down here, right? AI1 times B1J plus AI2, that's this guy, times B2J, that's this guy. We go all the way out until we're out of entries. And now maybe you see why you have to have the same number of columns in A as you have rows in B. Because the number of columns in A tells you how many entries are in this row, and the number of, let me say that, make sure I say that right. Number of columns in A are the number of entries in this row, and the number of rows in B give you the number of entries in this column. Kind of seems strange to say it out loud, but that's really what's happening. So that's how I think of it. To get this ijth entry of the product, I think of laying the jth column of B over the ith row of A, taking those component-wise products and adding them all up. Here. Another quick compact way of expressing this is to say that your matrix product of A and B, AB here, the ijth entry of that is defined to be the sum from k equals 1 to r of aik bkj. So if you notice, that really fits this form of this sum. It's like this index that's increasing through the sum, the 1 here, the 2 here, all the way up to the r here. That gets replaced by a k in the sum because that's what we're stepping through, is value 1 for that, value 2 for that, value all the way up through value r for that. So we let k go from 1 to r. But we notice the a's in all of this stuff always have an index I, and the b's in all of this stuff always have a column index of j. So we step through those inner indices, keeping the outer indices fixed, and that's another nice way to write this product. We'll see that all these sort of notation details really won't be that important when you're actually multiplying matrices. They're more important for proofs. But for now, let's just see how this actually works. So using those same matrices, B, C, and D that I wrote down in the previous example, over here, I want to go through a little bit of matrix multiplication and make sure we see how this actually works. So first, D times B. I've copied those matrices here. This is D, this is B. The first thing we should look at whenever we're multiplying matrices, the first thing we should look at is the size of the matrices. Make sure it actually makes sense to be multiplying these. Notice D is size 2 by 2. Right, it's 2 by 2. B, this matrix here, is 2 by 3. And this is exactly what we need. The number of columns in the first matrix in the product, D, is equal to the number of rows in the second matrix in the product, B. So you might think of this as being, when you write it out the way I have over here, you might think of needing the inner dimensions matching. Right? You need those to match in order to multiply. They do in this case, so we can actually perform this multiplication. We will do that. What we also want to notice is that the result of this, D times B, will have the outer dimensions as the result. Right, so result of the multiplication, so the product, I should say, as size given by outer dimensions. So 2 by 3 in this case. You think of the inner ones as kind of canceling out, they become irrelevant so long as they matched. Then you're left with something of the size given by the outer dimensions. So we're going to have a 2 by 3 matrix. 2 rows, 3 columns. So let me fill these in. First row, first column says take the first row of the first matrix in your product, D, and multiply that with the first column. When I say multiply that with the column, I'm really just saying 2, 2, that's our row. 2, -1, that's our column. Think of laying this over this guy, doing those pairwise products and adding up. So 4 plus -2 equals 2. That's what goes here. What about the next entry? First row, second column. Well, that says I'm still using the first row here, but now I'm using the second column. So I'm going to lay 2, 1 over this guy. Do my work on the side here. Right, lay this column over here. Take those pairwise products, and then add. 4 plus 2 gives us a 6. And in this way, we'll just continue out the first row. So to get that last entry in the first row, that last column, I'm just going to the last column here, right? This is first row, third column. First row, third column. That's the entry we're trying to find. So let's try to find that. I'm taking 3, 1 and kind of laying it over 2, 2. What am I going to get? 6. So 2 times 3 is 6, plus 2 times 1 is 2. 6 plus 2 is 8. If you've seen dot products, all I'm doing is dotting the row we're on with the column that we're on. That's all we're really doing. We'll talk more about dot product later, but if you've seen that already, that might be the best way to think about this. So now to handle, say, to handle the entry right here, bottom left corner, that is in the second row, first column. So I'm using this guy and this guy. 2 times 4 is 8, plus 2 times -1, that's a -2. 8 plus -2 is a 6 here. And so on. So the next entry means I need to move down the column here, and then the next column over. 8 plus 2 gives me a 10 here. Use my eraser. 10 here. And finally, 3, 1 laid onto that row of 4, 2 gives me 12 plus 2 is 14. So there it is. There's the product D times B. It's 2, 6, 8 in the first row, 6, 10, 14 in the next row. Hope that kind of clarifies what all this talk up here was really about. The notation can be intimidating, but really the process isn't so bad. Okay, so I'm going to go through this one a little bit quicker. B times C. This is 2 by 3, 2 by 2. We have a problem. We have an inner dimension mismatch. 3 and 2 don't match. This product is undefined. So we're done. We move on to the next one, C times D. Right, so that's why I say you should always look at those matrix dimensions first to make sure they actually work for multiplication. If not, you're done right away. What about C times D? This is 2 by 2, 2 by 2. Inner dimensions match, meaning the outer dimensions give the size of the result. 2 by 2. So we have 4 entries to figure out, right? Top left, top right, bottom left, bottom right. So let me figure those out. In the top left, I have first row, first column, 1, 1 with 2, 4. Laying this guy over and multiplying gives me 2 times 1 is 2, plus 4 times 1 is 4. I get a 6 here. Next entry in that first row of the result is going to be now the column 2, 2 laid over on that row, which will give me a 4. 2 times 1 plus 2 times 1. Now, if I want to go to the bottom left, I need to get into the second row, first column. 4 plus 4 is an 8 here. And finally, first row still, but now last column. It looks like here I get 4 plus 2 is 6. So C times D is 6, 4, 8, 6. Now we're going to see something kind of interesting here. We just did C times D. Let's take D times C. We want to see something very important here. Still 2 by 2 with the 2 by 2. This is still well defined. My outer dimensions tell me the result will still be 2 by 2. Now let's see what we get. Top left corner is going to give me 1 times 2 plus 2 times 2. Top right corner is going to give me 1 times 2 plus 1 times 2. Bottom left, that's first row, first column. That's 4 plus 4 is 8 here. And finally, what do we have in the last? 1 times 1 and let's see. Oh, there we go. We get a 6. 1 times 4 and 1 times 2 added. That was this row, this column. So notice, oh my goodness, we got the same thing, which you might say, well, that's just intuitive, right? You multiply CD, multiply DC. Well, we know from handling numbers, just real numbers, that works. You get the same result. Well, I claimed that what happened here was actually a fluke, right? In general, it's not true that AB equals B times A. We just saw one particular case where that occurred. And what really made that happen here is that this matrix D is really 2 times 1, 1, 2, 1, which is just 2 times C. So it turns out in this case, whether we wrote it as C times D, or really what it is, C times 2D, sorry, C times 2C, right? D is 2C. We see that the order really doesn't matter just because it's the same matrix we're multiplying. Less this constant, but that matrix part is really the same stuff, just with the scalar attached. So if I reverse this, really the actual matrix stuff is being multiplied in the same order it was before. C times C can only be written in one order. It's always C times C. But in general, I want to make it clear, A times B does not equal B times A. This is a huge important fact that we'll talk about throughout this term, but AB does not equal BA. So we'll use that to really ingrain it into us that we can't assume these are equal. We'll use that fact later in an example, but for now we just need to remember AB is not the same as BA. Matrix multiplication is not commutative. That's how we would say that. Okay, let's look at some special matrices. A 0 matrix has all 0 entries. We usually denote that by 0. And if it's a square matrix, we might write n here, where n is the number of rows and columns that the matrix has. So if I wrote something like 0, 2 here, that would imply that we're talking about 0, 0, 0, 0. Right? That's all we get. So that's one very special matrix, the 0 matrix. There's also a diagonal matrix, is a very specific type. It's really just a square matrix with only 0 elements off the main diagonal. For example, something like 2, 0, 0, 0, 1, 0, 0, 0, negative 3, just making stuff up. That would be considered a diagonal matrix because only off the main diagonal, I should say, we have only zeros. Right? 2, 1, 3 along the main diagonal, zeros elsewhere. That means this is a diagonal matrix. Okay. It is important we say this is diagonal if we had numbers across the opposite way, like top right down to bottom left. We might call that an off-diagonal matrix or just not refer to it as diagonal. Very important matrix that we've already seen a little bit about, the identity matrix. is the n by n diagonal matrix with ones on the main diagonal. So if you've got something that's diagonal, this sort of form, but it's got all ones there along that where the non-zero entries are, that's called an identity matrix. If it's n by n rows and n columns, we usually denote that with I subscript n. You'll notice we often just leave off the n if the dimension is implied by the problem. Okay, so let's go further with talking about matrix multiplication. Oh, in fact, I forgot something. Why do we care about these special matrices? Well, we care because of these three facts up here. They give us really some power to perform some algebraic manipulations. For example, A plus the zero matrix or the zero matrix plus A is still A. So long as these additions make sense in terms of the size of A and the size of the zero matrix you're working with. Right? If this is 0 mn, we're implying it has m rows and columns. A better have the same dimension. But so long as it does, adding the zero matrix to A from either side doesn't change A. Likewise, multiplying a matrix B with the zero matrix from either side, so long as the dimensions make sense for matrix multiplication, will always result in a zero matrix. Try this out and see very quickly why that is. Easiest reason to see is that in every entry that has this form up here, either the A's or the B's will all be zero values. So they'll zero out every entry. Okay, and finally, why do we care about the identity matrix? The identity matrix works for matrix multiplication the way that the number 1 works for scalar multiplication, right? It is known as the multiplicative identity. That's why we call this matrix the identity matrix. When we multiply by it from either side, so long as the matrix dimensions make sense for the multiplication, to be well defined, if we multiply from either side, wasn't happy with that. If we multiply a matrix from either side by the identity, so long as the matrix multiplication is well defined, the matrix we multiplied the identity on is unchanged. It's just like multiplying by 1, but the matrix version of that. Okay, important to note that, but let's move on. So a couple of notes on matrix multiplication, different ways you can think about it, some useful ways to think about it. One useful way is to write the matrix B, if it's an m by n matrix B, write it in terms of its columns, B1, B2 through Bn. So if I have my matrix B with the usual entry labeling system, the IJ subscript notation, my B1 column would look like this, B11, B21, down to BM1, right? Where you're going through all the different rows, row 1, 2, down to M, but you're staying in that first column for your second index. That keeps you in column 1 of B. We call that B1. And so on for the other columns, right? So if we think of B that way, then multiplication AB, a matrix A times B, really produces a resulting matrix, a product matrix C, with columns CI equal to A times the ith column of B, right? We're saying if I multiply A times B, the result of that multiplication, the result of this product, the ith column of that result is just matrix A times the ith column of B. This is really nice. It gives us a nice, easy way to break down some of these complicated multiplications. Right, so here it is more visually, I think, easier to see. AB is the same as A times this matrix, where we write its column names instead of the actual entries, B1, B2 through Bn. And then it's kind of like, I don't want to say distributing, but it's kind of looks like we're distributing, right? A multiplies on B1, A multiplies on B2, and we get this new matrix, right? The first column of the result is just A times the first column of B. The second column of the result is A times the second column of B, and so on. So let's see this. If we want to multiply the matrix A equals 1, 2, 3, 4 by the matrix B, which equals 3, 4, 2, 3 in the first row, 1, 4, negative 1, negative 2 in the second row, and we want to do that with this sort of method, multiplying by B1, B2, B3, and B4 separately. Well, what are we really doing? Following this sort of format laid out up here, we're really saying that we can write this matrix product as 1, 2, 3, 4 times the first column, 1, 2, 3, 4 times the second column, and on, right? Notice I'm not putting plus signs between this. These are making the entries of our final result. This is one big matrix that I'm writing matrices within. Continuing on, 1, 2, 3, 4 times 2, -1. The last row here, the last column here will be 1, 2, 3, 4 times the last column. And so I've kind of written all these pieces down here, except for the last one. I don't know why I left that out. Figure that out. But all we want to do is these simpler multiplications, right? This is 2 by 2, 2 by 1, so the result's going to be 2 by 1, those outer dimensions. So it's really just two entries made into a column. The first one says take the first row of A and lay this column of B over it. 3 times 1 plus 2 times 1. Yeah, this looks right. Looks like I get a 5 there. Oops. Wasn't sure about that. Looks good. Okay. For the next entry, we take the next row and lay that column over. 3 times 3 is 9, plus 4 times 1 is 9 plus 4. I get 13 here. Man, I'm having a hard time. 5, 13. There we go. And I'll continue with this multiplication the same way. 4 times 1 plus 2 times 4, I get 12. 4 times 3 plus 4 times 4. Looks like I get 28 there. Check my work. 2 plus -2 gives me a 0. 2 times 3 is 6, plus -4, I get a 2 here. And finally, A times B4 is this matrix product. What do I get there? It looks like 3 plus -4, 9 minus 8. And so there we have it. We have all the columns of the product. We can just write it down now. 5, 13, 12, 28, 0, 2, -1, 1. And by the way, you can do these multiplications, matrix A times B in Octave or MATLAB, certainly. You just want to write a little star for the multiplication. And so enter matrix A, enter matrix B, and then at your command prompt, you can enter A star B to multiply them. It certainly knows how to do matrix multiplication, quick and easy. Great way to check your work. Great. So this is one nice way to think of A times B is really A multiplying on all the columns of B individually. Right? That gives you your final matrix. Okay. Another way we can think of breaking it down is what I've got coming up next here. The multiplication of matrix A, which is M by N, where we write A in terms of all its columns, A1, A2 through AN. If we multiply that matrix A on a column matrix B, so this is just a single column, there's only one column in matrix B, it actually produces a linear combination of the columns of A. Really just sums of these scalar multiples, the first entry of this column B times the first column of A, plus the next entry of column B times column A, times the next entry of B times the next column of A, and so on, all added up. So writing it out visually here, AB is the same as writing A with all its columns. Writing B's entries down, it's assumed that B is a column vector. Sorry, got to sneeze there. We just get the first entry here times the first column here. So A1 times B1. Then A2 times B2 all the way out through AN times BN, all added up. And you can check this works out if you do standard matrix multiplication. Usually we'd write in a linear combination like this, right? The A's are columns, the B's are scalars. In a linear combination like this, we'd write the scalars first typically. So we might write it this way, you see here. Well, this is pretty easy then if I want to use this to multiply AB in this example. All we have to do is take each column of A times each entry of B. 2 times the first column, 3 times the next column, plus 2 times the last column. Pretty easy. Scalar multiplication, 2 multiplied on a matrix, 3 multiplied on a column matrix, 2 on a column matrix. The pieces here are easy, right? What do we get? 4, 6, 2, plus 9, 3, negative 3, plus 0, 2, 2. Easy to add these up. Adding across the first entries, 4 plus 9 plus 0 is 13. Next entries give me 9 plus 2 is 11, and finally 1. So AB equals 13, 11, 1. And we're done. So if you haven't seen it before, we can always view matrix multiplication by a column matrix to the right in a very simple way like this. Now to end this section, I want to talk about one more kind of clever way to break up this multiplication. And this gets into partitioning matrices. So that idea is discussed here. Matrix A can be thought of, spelling is terrible here. Matrices. Yeah, a matrix A can really be thought of as consisting of smaller matrices whose entries are really just submatrices of A. Really, we call these blocks of A. So for example, if I had a matrix A that looks like this, I can put a vertical line between any 2 columns and a horizontal line between any 2 rows, and look at how that's created blocks of numbers in my matrix. I can give each block a name as its own matrix. I'll say P is this 1 by 1 block that just equals 2. I'll say Q is this 1 row by 3 column block, 1, 3, 4. I'll say R in the bottom left is this 2 row by 1 column block, 1, 0. That's my R here. And S is this remaining block, 1, 2, 1, 2, 3, 1. So if I do that, I can really think of A as having these individual, you can kind of think of them as individual elements that are really matrices all their own. And what's great about this is it turns out if you've got 2 matrices partitioned this way, that's what this is called, it's partitioning A, then you could actually think of multiplying the 2 matrices just like you would multiply these elements here, only they will give matrix multiplication instead of the scalar multiplication we're used to. So let's see a little more about that. That's described here. If A is M by R and B is R by N, and they're partitioned in any way so that the necessary blocks have dimensions that allow them to be multiplied, then the partitioned matrices can be multiplied as usual by treating their blocks as usual entries. So I've got an example started here. We'll finish it up. If I have the matrix A partitioned this way, right, where I'm calling the top left A11, top right A12, usual lettering system for my entries, right, usual subscript system here. A21 is this 1, 0 column, and A22 is this remaining block out here. Notice I'm not putting little brackets around these A's before I put the subscripts. That would mean I'm talking about the entries of A, instead leaving capital A with the subscripts and no brackets. And I'm writing, oh no, what happened? Okay, let me fix that. Sorry. Right, notice I'm writing A11 equals this little matrix. If I wrote A brackets around that 1, 1, that would indicate that I'm talking about the 1, 1 entry of matrix A, which is just the number 2. That one's kind of by coincidence, not a big problem, but if I did this with, say, a 2, 1, a 2, 1 is a matrix. If I put brackets around A and then label 2, 1, that's the 2, 1 entry of matrix A. Row 2, column 1, that's equal to just 1. So the notation here is pretty careful. Putting brackets inside would be bad. That's bad. Okay, so anyway, if I partition A this way, and I have another matrix B that I partition, I've chosen B to be this matrix, 2, 3, negative 1, 1, negative 3, 0, 5, 1. And I've just partitioned it just into two pieces, the top row and all the bottom rows put together. So B11 is this first entry. I'll call that just the row 2, 3. And B21, the next entry down, again, I've kept that usual subscript indication, the usual index notation here. Pretty standard, and I'm calling B21 all this remaining stuff, negative 1, 1, negative 3, 0, 5, 1. Now let's see, to multiply these using partition matrices, what we're really doing when we multiply matrix A with matrix B, now that we're thinking of partitions, matrix A just looks like this, so I've written that here. Matrix B looks like this, so I've written that here. And it turns out, since all the dimensions make sense, right? This has 2 blocks by 2 blocks. This has 2 blocks by 1 block. Inner dimensions agree, even though they're talking about matrix entries. They agree. Outer dimensions give us the size of the result. It should be 2 by 1. 2 rows, 1 column. I just wrote a big, wide column here. Well, how do we come up with the entries of this resulting column? Same way as before. For the first row, first column, we take the first row with the first column. So we take all this stuff and kind of think of laying it over here. We do want to think of the A's as being to the left of the B's, so that this would imply A11, B11, this guy with this guy, laying it over, plus A12, B21, this guy with this. Right? And A21, B11. Now I'm laying this down onto the other row. B11 plus, it lays down over here, A22, B21. Now, whether this is easier, I wouldn't necessarily guarantee, but certainly it is a clever way to break down these complicated matrix multiplications in a way that's not requiring we learn a lot of new process here, right? We wrote this out just as if all the blocks were actually numbers, but they're not. They're blocks they're matrix blocks. So if we want to do this, all we have to do is compute these 4 little matrix products, which I will do out on the side over here. We need A11, B11. A11 is just 2. B11 is 2, 3. You can work it out. Matrix multiplication in this case just gives you 4, 6. We also need A12, B21. What is this? B21. This one actually requires some work to multiply out. Do the dimensions work? Yes, this is 1 by 3 out front, 3 by 2 out back, inner match. So we get the dimension of the outside numbers for the result, 1 by 2. So what happens here? To multiply this out, right, this is 1 by 2 columns, 2 entries to fill in. In the first entry, we take the first row with the first column. -1 times 1, -3 times 3, and 5 times 4. It's like this gives me a +10. And the next, it looks like I get 5. You can check my work there. Oops. 3, 0. A little wild with the eraser there. Fix this up. Okay, moving right along. Well, maybe let's finish this up for the first entry of our product down here. A11, B11 plus A12, B21 equals 4, 6, plus 10, 5, easy to add, 14, 11. So there we have the first row here. What do we have left? A21, B11, A21, B11. I'll go ahead and do this one. This is 2 by 1, 1 by 2. The result will be 2 by 2. Looks like here we get first row, first column makes 2. First row, second column makes 3. And it looks like first row with any column will give us 0. Okay, almost there. A22, B21. A22 is this guy. B21 is this guy. Two by 3, 3 by 2. So the result is again 2 by 2, which is good because we're trying to add this to the other 2 by 2 we got. So what do we have? First row with first column gives me -1, -6, plus 5. Looks like -2 there. If I move over to the next column of that first row, I'll get 1 plus 1 makes 2 there. Second row now, first column. Looks like I get -2, -9, plus 5. What does that make? -6. Finally, last row, last column, 2 plus 1 is 3. So here we have it, but we are asked to add these to get the end of our, get the bottom of our matrix here. So what do we have? Adding gives me 0. We're adding these two. Adding these two matrices. You get 0, 5, -6, and 3. And there we have our matrix product fully computed. Right? And so you might say, well, I thought this was supposed to be 2 by 1. Well, it was 2 by 1 in these blocks. But this first block up here, we saw each of those was a 1 by 2 matrix. The second block down here, we saw each of those was a 2 by 2 matrix. So yeah, this was a 2 by 1 in blocks, but it actually came out to 3 by 2, as it should if we look at these guys. 3 rows, 2 columns means AB will have 3 rows, 2 columns. So this process here, this is called block multiplication. You won't use it a huge amount of the time, but it is certainly useful for some proofs here and there and some manipulations of these multiplications of matrices can be useful just when you're dealing with numbers, not even in proofs. So that's it for this video. Thanks for your attention. In the next one, we will see more about matrices. Thanks again.